all of these, so we'll just fill that in. All right, so going from carboxylic acid to acyl chloride, you use what? You use Sokol. You can use the PCl5, but Sokol is more loved by Dr. Roche. So this is going to be the basis for most of like the transformations between the derivatives, because the acyl halide is the most reactive carboxylic acid derivative. So a carboxylic acid is not that reactive. So you want to turn it into an acyl chloride before you turn it into something else. So you can just do the reaction much more easily. So yes, so starting from an acid chloride, you can go to basically every single carboxylic acid derivative. So if you give an acyl chloride water, what derivative do you think you're going to get? Carboxylic acid. All you have to do, you have to cut off this leaving group, cut off one hydrogen from the nucleophile, and then just replace the nucleophile where the leaving group was. So we identify leaving group as chlorine. We're going to lose a hydrogen in the process of the attack from the H2O. So that nucleophile is going to attach itself as an OH. So now you have a carboxylic acid. Then your side product is HCl, but it's a side product, so no one writes it. Another thing you can do with acid chlorides, which does kind of show up on exam 3, is a Friedel-Crafts acylation. So you remember with Friedel-Crafts acylation, no. With Friedel-Crafts acylation, you start with an acyl chloride, and then you have a Lewis acid catalyst, and then like any benzene that has an activator or just a plain benzene. And then this way you can go from an acyl chloride to a ketone. So remember, you just cut off the chlorine and then attach the acyl group somewhere on the benzene, wherever your directing effects are. So then you just get a ketone with a phenyl on one side. Okay, and then you can also, wait, what's the point of this? Okay, so you have an acyl chloride and water, but you also have a base. So the base just means that the solution that you're doing this reaction in is in basic conditions. Did he talk about basic versus acidic conditions at all? Okay, then you probably don't have to be concerned with this, so we're gonna move on. The next thing you can do with an acyl chloride is give it a carboxylic acid salt. So when you see RCOO-Na, you just know that it's a carboxylic acid ion. So it looks like this, and then it has an Na attached to it. So they're stabilizing each other by an ionic bond. So this ionic form of the carboxylic acid is nucleophilic, has a lot of electron density. So it just goes ahead, it's going to attack the carbonyl, and you can do the exact same thing. You just cut off the leaving group and replace it with your nucleophile over here. So by doing that, what carboxylic acid derivative do you think this yields? Yeah, anhydride. So you're adding like another carbonyl or ester group onto the existing carbonyl. So if you have two carbonyls, oxygen in the middle, it's called an acid anhydride. So this portion came from our nucleophile up here. And then we'd probably have NaCl floating around in solution as your side product. All right, so the next one, what do you think happens if we give an acyl chloride and alcohol? Huh? Yeah, carboxylic, but instead of an OH, it's an OR. So it becomes an ester. So remember, you cut off leaving group, cut off one hydrogen, and just attach whatever's left from the nucleophile. So we cut off the Cl, and we know we're going to attach an OR. So if we have an acyl group with an OR attached to it, we know this is an ester. So now if we give acyl chloride some kind of amine, so the amine can be in three forms. You can have it as ammonia, so NH3. You could have it as a primary amine, so it'd have two hydrogens and one R group, or you could have it as a secondary amine like this. Tertiary won't work, but you can have those three forms. So whenever you see like an N something, just know it could be either of those options. So in this case, we're giving an acyl chloride a secondary amine. So what derivative would that give you? An amide. So once again, chop off the hydrogen, chop off the chlorine, and cut and paste. Okay, so now we have a carboxylic acid and we're trying to turn it into this amide. So one way, well, what are two ways you could actually do this transformation? And you have to consider the order of reactivity.
You put a chlorine on it first?
Yeah, that would certainly make your life easier. So we'd use Sokal 2 to do that. And now you have an acid halide. So now can we go from the acid halide to that specific amide? So you're just going to have an H2N and then whatever this R group was. So remember, in the process of this reaction, you lose one hydrogen from the nucleophile. So if you're doing retrosynthesis, to find a nucleophile, you basically just like find out what replaced the original leaving group and then like add a hydrogen to it. So we know that we gave this acid chloride a primary amine. And then that's going to give you that final product. Okay, so after acid chlorides, the next most reactive derivative is your acid anhydride. Yeah.
So can you go straight from the acid to the amide?
You could go straight. So you know the order of reactivity, that tells you what you can go from easily. So the carboxylic acid is more reactive than the amide, but not by much. What would be much easier to synthesize would be going from carboxylic acid to acid chloride. And then an acid chloride reacts very quickly. So you could go from that very easily all the way back to an amide. But since carboxylic acid is more reactive than an amide, you could go directly. Okay, so for acid anhydrides, we're trying to go from a carboxylic acid to an acid anhydride. All right, I'm sorry. So is a carboxylic acid, going from a carboxylic acid to an acid anhydride, thinking about that order of reactivity, would this direct transformation be favorable?
It's not favorable.
Yes, it's not favorable. So in this case, you're not going to go through an intermediate. In this case, we're going to make the carboxylic acid the nucleophile. So usually if you see like a reagent here, and it's being transformed to something, you think that like on this reagent line, we're going to have a nucleophile. But in this case, we're just putting the nucleophile down here. We're just rearranging it a bit. So what we're going to do is mix this with an acid chloride. And yeah, we're going to give the carboxylic acid an acid chloride because that's the easiest way, that's the easiest carboxylic acid derivative to attack. So if you add an acid chloride, the carboxylic acid just goes in and attacks, and then you do the same deal. You cut off the leaving group, cut off a hydrogen, and just paste them together. So you couldn't do the same thing you did with an acid chloride. Like you couldn't just go ahead and attack this carboxylic acid with like an acetate ion because the carboxylic acid is not reactive enough. It's not electrophilic enough, and it doesn't have a good enough leaving group. So we're going to have to use that to attack something that is more reactive.
What if you use solvent to make it CO?
That would work. Yeah, you could also do this in 2 steps. Or you could just do like 2 equivalents of the acid and then 1 equivalent of Stockl. So you get half and half and just mix them together. All right, the other way to make acid anhydrides is if you have a dicarboxylic acid. So let's say you have like a carbon chain that has a carboxylic acid on either side. What you need to make sure first is that you have like a good enough amount of carbons in the chain. So in this case, there's 4. So there's 4 carbons. You're gonna end up with a 5-membered ring. A 5-membered ring is favorable because the bond angles are nice. Like all the atoms are happy, there's no ring strain or anything. So it's going to be more preferable with like 5 to 6 to 7 carbon chains. So in this case, all that happens is that you heat it up at like 300 degrees and you basically just cut off one of the alcohols and like rejoin them together at another one. A better way to think of that is like one of the alcohols went in and attacked, and then the other one just left. So now you have a cyclic acid anhydride. And I think I saw this being used as like a Friedel-Crafts thing. So in like one step, you'd have to know that heat is what does this transformation. And then in the next step, he'd give you like a benzene and then a Lewis acid catalyst. And then you'd have to know that you can do a Friedel-Crafts reaction with an acid anhydride as the electrophile. And then he'd probably make you do like a decarboxylation on that. So just be aware this can go to Friedel-Crafts acylation. So the acid anhydride is pretty reactive. The only thing that's less reactive then is the acyl chloride. So it can basically turn into all the carboxylic acid derivatives besides the acyl chloride. So it's the same idea here. You identify the leaving group, identify the nucleophile, cut off the leaving group, cut off a hydrogen, and just cut and paste. So for the first one, we have an acid anhydride and an alcohol. So what product does that give you? An ester, because you're replacing this leaving group with the OR nucleophile. Huh? Oh, like you can't go from an anhydride to an acyl chloride. If you convert it from an anhydride to a carboxylic acid and then use Stockl, that's like the only way. These reactions are pretty straightforward in that you just cut and paste the entire time. The only thing you have to kind of like critically think about is the order of reactivity and what is easy to go, like which derivatives it's easy to go from. So the next one, we have an acid anhydride and we're giving it a secondary amine. So what happens here again? You're just going to cut and paste. So you get an amide. And then the third one, what do you think happens if you give an anhydride water? You get carboxylic acid. So get rid of 1H, get rid of the leaving group, and you get your carboxylic acid. And then lastly is the same thing, but in basic conditions, but we don't have to worry about that. So,
Just get the alcohol, like, what do you do after just get the alcohol, not carboxylic acid?
oh, like to make an alcohol from a carboxylic acid derivative.
Yeah, so say you have a anhydride, you want to make the alcohol. How would you do that?
So I think this would take 2 steps. I would first turn the anhydride into an ester. And then when you cleave the ester, because you cleave it at this point, you're gonna get like a carboxylic acid product and then your alcohol product from the OR. I think that's the only way to do that.
And you would use R8OH as well?
ROH, I mean, that wouldn't, as a reagent to make the initial ester, yeah. But then in the second step, I would use water, because if you use an alcohol in the second step again to like cleave this thing, you'd get a carboxylic acid product and an ether, which is not what we want. So to make esters, you can use Fischer esterification. So notice how the other reactions we did, they were single, they're just one arrow. It only goes in one direction mostly. But for Fischer esterification, we're going from a carboxylic acid to an ester. And they're going to be at equilibrium because carboxylic acids and esters have like the same reactivity. So it's going to be switching back and forth between the 2 derivatives. So in order to shift the equilibrium towards the ester, you need excess alcohol, and you also need an acid catalyst. So for the acyl chloride and acid anhydride, to turn those into esters, we did not need any acid catalyst. We could just use a plain old alcohol. But because esters and carboxylic acids have such similar reactivity, we need something to speed that reaction up. So now that we have the acid catalyst and also excess alcohol, we can do the same thing. We can cut off 1 hydrogen, cut off the leaving group, and paste it. And the way you ensure you have the most ester product is by adding a lot of alcohol in excess. If we wanted to go back from an ester to a carboxylic acid, what do you think we would replace this nucleophile with? With water, yeah. So in that case, if we want the equilibrium to go to the carboxylic acid side, we just add a ton of water to this reaction and keep everything else the same. Okay. So other methods to get esters, you can use the more reactive derivatives like in acid chloride, and you can just do your usual cutting and pasting here. So with an acid chloride, cut off the chlorine and then add the OR, you get your ester. And remember, it's the exact same thing with the anhydride. the leaving group goes, the OR goes on. All right, so if we start with a cyclic acid anhydride, and we give it an alcohol, we're going to end with a different product on each side. So when this anhydride cleaves open, you're gonna have two carbonyls on either side. So we're just gonna go in and attack one carbonyl with the alcohol. So we're gonna say it opens up like that. So on top, you have an ester because you just attacked with an OR. But on the bottom, you still have this ion floating around. Actually, wait. So for now, let's just say that the OR is still protonated because the nucleophile was an ROH. So let's say it attaches to the carbonyl as an ROH. Conveniently, there's an alkoxide ion down here. What happens is that the alkoxide just takes this proton from the alcohol and it protonates itself. So now on top, you have a plain ester, and on the bottom, you have a carboxylic acid. So when you do normal acid anhydride hydrolysis, turning an acid anhydride into an ester using an alcohol, you get two products. You get the ester that you wanted, and you also get carboxylic acid side product because that's the leaving group. It's a carboxylic acid ion. So when you have them together, if you have two carbonyls and an anhydride in one molecule, you get those two products, but they're just stuck on the same molecule. I don't think so. I think you just get like your mixture and then isolate the one you wanted. Like which part? Okay, so when you're hydrolyzing an acid anhydride, usually you get two main products. You get one side, which was the ester, which was like successfully attacked by the alcohol. Then you get your other half, like this leaving group that got cleaved off. It gets protonated basically, and you have carboxylic acid side product. So because we have a cyclic acid anhydride, you get your ester and carboxylic acid stuck together on the same molecule. So usually we're not concerned with the carboxylic acid product, but since it's cyclic, we have to be concerned with it. And then the very last one is just ester hydrolysis. So we're going in with water and hydrolyzing, or just like splitting the ester open. So what happens here is basically that the base is just going to go ahead and attack. And yeah, you get your carboxylic acid because this OR group is just going to leave. And then as a side product, you have that OR group floating around and it gets protonated by the water or the acid, and you have just ROH floating around in solution. When you hydrolyze an ester, you get carboxylic acid and alcohol. It's all just part of the mechanism.
You just switch water and not the base.
Probably wouldn't be too, you'd probably have a really low yield. You're gonna need the base to like speed up the reaction. So yeah, that's why you use that as a nucleophile. And then you use the water like to keep the equilibrium towards carboxylic acid. Okay, so lactones are just cyclic esters, and there's some naming conventions and all that. Did he tell you about like the Roman numerals and counting lactones? Oh, nice. Okay. So basically, this is the same thing that we did above. It's going to be like ester hydrolysis or carboxylic acid hydrolysis, basically. So what you're doing is that you're forming a cyclic ester. So to do that, you need to have an intramolecular reaction. So you need your nucleophile, this alcohol, and your electrophile, your carboxylic acid derivative in the same molecule. And the thing for lactone formation is that you also need like an appropriate amount of carbons in between. So we have like we have like 4 carbons here. And then counting these two, it's going to be total like a 6-membered ring, which is very favorable. If you had a much shorter carbon chain, say like like 3 carbons or 4 carbons, that would give you, or that reaction wouldn't really happen because the ring strain is so unfavorable. And he didn't mention like alpha, beta, gamma lactones. Nothing. So I'll just count that. Yeah, there's like a special way to count number of lactones and lactams, but we're not concerned with that. So basically, all that happens, carboxylic acid, alcohol are in the same molecule. You give it an acid catalyst, and then this alcohol goes in and attacks the carboxylic acid. And that attack just forms a ring, and you get a cyclic ester with water as a side product.
You mentioned something called activates something.
I don't know what those are.
Techniques.
Hmm?
Instead of those are techniques.
Carbonate. Oh. I've never heard of that. And I wasn't in lecture, so I can't really tell you much about that. Wait, does that mean like DCC? All right, we're just gonna ignore it. Oh. Next, it's the same thing. We're making a lactone, but we're just counting it differently. So up there we had more carbons in between the nucleophile and the carboxylic acid. Here we just have 3. Yeah, so we just do the same thing. We attack with alcohol and turn this into a cyclic ester, and we form our ring. So there's 3 carbons in between the carbonyl carbon and the alcohol, or the free OH. 1, 2, 3. And then our oxygen is here, and then we just draw in that new bond. All right, so to make amides, amides are the complete least reactive carboxylic acid derivative. So it's very easy to go from literally everything else to an amide. All we have to do is just use an amine as your nucleophile, and adding that to any of the other derivatives is going to give you an amide. So acyl chloride plus any amine. Remember, when we have an amine, it could be an NH3, H2NR, your primary, or your secondary. And then all 3 of these are going to give you an amide. So for the first one, cut off the chlorine, cut off the hydrogen, and you get your amide. Maybe the thing you have to be careful with is like differentiating 16 and 17. So in 16, we had like aldehydes and ketones. And when we gave aldehydes and ketones amines, they would turn into like amines and enamines. But in this case, if you give like a carbonyl with a leaving group and amine, you get an amide. So just be careful.
What? I'm sorry.
Yeah, so if you just have to look at which carbonyl you're starting with. So if you're starting with like an aldehyde or a ketone, and if you give it an amine, it turns into like an enamine, amine, oxime, whatever. But if you have something from chapter 17, like a carboxylic acid derivative, then you know the amine is going to like do the nucleophilic attack and turn into an amide. So like there were some cases where I saw a ketone and was like, oh, we're gonna make an amide, but no, we were just like making an amine.
How would you differentiate?
Well, you have to look at which carbonyl you have. So if this chlorine was not a chlorine, and if it was just another R group, then it would be enamine formation. But we have a Cl, so it's amide. So same deal with non-cyclic, with acid anhydrides. So just cut out the leaving group and paste on the amine.
It says it's 2 equivalent. So what? Then would it still form?
Oh yeah, why did I put 2 equivalents? I must have had a reason. Oh, okay. Yeah. So you have an anhydride. So this whole thing is like a carboxyl derivative leaving group. So in order to get like your full yield of one product, you kind of have to get the full yield of the other product. So you want to like fully hydrolyze, or I don't know, the amino equivalent of hydrolysis. You want to fully break apart this anhydride. So we have to consider the side product. So when this whole thing leaves, you get, this is your side product. You get some kind of carboxyl like ion. What happens here is that this has to bond with the amine to give you like an ammonium salt. So this is gonna be like ionically bound to NH2R1, R2 plus. So in order to like satisfy the leaving group and have like that stabilize, you're gonna need to use 2 equivalents of the amine. Because more of the amine might go to this side of the anhydride and not enough might go to this side. But I think just safe to assume it's in excess if there's nothing written there. All right, and lastly, we can go from an ester to an amide, because an ester is more reactive. This reaction is kind of slow, but it still works. So same thing, cut off alcohol, add amine, and you get an amide plus an alcohol side product. And to make lactams, it's the exact same thing as making cyclic esters. So lactams are cyclic amides. So am is amide, yeah. So basically it's the exact same idea. You have your nucleophile, which is the NH2 in the same molecule as the electrophile, your carboxylic acid. So what happens when you give it an acid catalyst is the NH2 just goes in and attacks the carbonyl. That color sucks. So it goes in and attacks the carbonyl. And then you're gonna lose the OH in the process and you get your amide. So there's 1, 2, 3, 4 carbons in between. Like the way I make the ring, I count the carbons in between and then I just like add 2 and that's like the number of members in the ring. So there's 4 carbons in between, 4 plus 2 is 6. So the final product is gonna be a 6-membered ring. So I just start by like drawing a hexagon. And I think it makes my life a bit easier. Because I really hate counting carbons. So you get your lactam and water. And this is going to be at equilibrium because the carboxylic acid portion is not very reactive. So it is going to be switching between like cyclic and linear. Okay, we have time for a couple of practice problems. Any questions before that on anything? Okay. So for the very first problem, you're starting with a carboxylic acid, and step 1, you give it Sockle 2, which does what? It turns it, yes. So it turns into an acid chloride. So you have an acid chloride and you have now this as your nucleophile. So what do we do with that? Yeah, you make an anhydride. So you take that nucleophile, it attacks, chlorine goes away, and then you get an anhydride. So now we're giving the anhydride some water. So what's water gonna do? And alcohol and carboxylic acid?
Just carboxylic acid.
Just carboxylic acids, but you get two kinds of them. So two different ones, because you have like one kind of R group on this side and then another kind of R group on this side. Yes, so you just split it in half. You get one acetic acid and then you get one propanoic acid. If we were using an alcohol, it would be a bit different because you get one ester and one carboxylic acid product. Okay, next one is a multi-step one and it's 349. I think we'll just end there. Oh wait, before you guys go, could you do me a favor and sign in?